welcome to the show. Today we're talking about the natural base E. Here's the basic idea of natural base. So we're going to be dealing with these LNs. We'll see if that shows up. Maybe. All right. Anybody? Bueller? I'm sure it'll show up in 10 seconds or so. There we go. All right, we're in, folks. So today, instead of log, you're going to see a lot of ln, which stands for the natural logarithm. So you might be solving something like ln x equals 3 or something like that. So just like when you have log of x, there's an invisible 10 down there, right? So with the natural logarithm, it's a variable, it's e. And e is just some standard number. I forget how they calculated it, but it roughly comes out to like 2.7 blah, 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 blah. A bunch of decimals. It's kind of like pi. It's just an irrational number. So oftentimes when you get these kind of problems, you know how earlier when we were doing like, if you had 3 to the x power equals 4, we were logging both sides. You'd say log of 3 to the x equals log of 4. So now if you have like e, you're going to ln both sides to cancel it out. So those are the inverse operations that we're dealing with the natural logarithm. You use that natural base e. So here, remember if you have an exponent, you could kick it to the front. So it'd be like x times log 10. And remember, there's an invisible 10 down there. So 10 to the first would give you 10. So it just becomes x times 1, which is x. Now over here, you kick the 3w to the front. 3w times log sub bb. If you have the same thing in the sub and the regular number, it just comes out to 1. So 3w times 1 is 3w. You'll start to notice a pattern here. Now, when your exponent is log sub the same number, which it's not written here, so that means there's an invisible 10, all that stuff cancels out, so you're left with just z. These are properties we're going to use today when we're solving some of these logarithmic problems with the natural logarithm and the base e. So the natural base e is just an irrational number, and it comes from this formula here, 1 plus 1 over n to the n power. So it comes out to 2.718, blah, 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 blah. It goes on. But it is an inverse operation, or inverse, we'll say operation, to the natural logarithm. So it's how we're going to solve equations when you're dealing with that natural logarithm, which just says ln. So here we're mixing in some old exponent properties. If you had e to the third times e to the fourth, you add those exponents, e to the seventh. Now here 10 divided by 5 is 2, and when you divide, you subtract the exponents. So 3 minus 2 is 1. So we just have 2e. Here we have to square everything. So 3 to the second power is 9, and when you go power to a power, remember you're multiplying them, so it would be e to the negative 8x. So 9e to the negative 8x. We're just bringing in all these old properties. We're mixing them in. Now here's our first thing with that natural logarithm. Remember, if it doesn't have a base written, that is a sub e. So if we kick our exponent to the front, negative 2t times natural log sub e of e. Now, just like when it was log sub 6, if it's the same thing there, it just comes out to 1. Same thing with the natural logarithm. If you have ln sub e of e, all of that just works out to 1 times negative 2t is negative 2t. So let's kick this 5 back. Let's make this e to the natural logarithm of x to the fifth. Now there's an invisible e down here. So this is that property where you're raising it to the exponent with the sub, same thing, all that cancels out, and you're left with just x to the fifth power. Again, invisible e down there with the natural logarithm, so it comes out to 1. With 4 more here. Okay, there's a sub e, right? The exponent we can kick to the front, so it becomes x minus y times ln sub e of e. All of this comes out to 1. So 1 times x minus y is just x minus y. We'll kick the 3 back, so e to the ln, invisible e, x to the third. All of this cancels out, so we're just left with x to the third. You're going to just see that same property. You're going to have e raised to the ln sub e power, and those all cancel each other out. Here we add the exponents, we get e to the third, and here we cube everything. 2 to the third power is 8, and then for the exponents we multiply, which would give us 8e to the 6th. All right, let's get into it. E squared. So you can chuck this in your calculator. It's usually in the same section as the logarithms, but you'll see ln. So that's where I find my e to the second power, which is, and again, e is like 2.718, blah, 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 blah. So e squared comes out to 7.389. And it goes on beyond that. 389. I'll just round to the nearest 1,000. E to the negative 0.06 comes out to 0.942. 0.942. Great. All right. So this is a lot like the logarithmic equations. It's the same problem. So here, we're going to condense it with multiplication because it has addition in the middle. So we would say ln of 5x equals 1. And then we're going to use that property that we always use, where you just drop in a new base. And the base is going to be the same as the sub number. So we're going to e both sides. So the e to the ln sub e all cancels out, so we just have 5x. E to the first power is just e, which, let's just do that in our calculator. So I always forget the decimal. 2.718. 2.718. I'm going to move over here because I know all these problems are on the left side. And then we just have to get rid of that 5 by dividing both sides by 5. Divided by 5 equals 0.544. X equals 0.544. All right. Here we have subtraction between them, so we'll bring it together with division. So we have ln of 5 over x equals 3. There's an invisible e in the sub, so we'll bring in a new base of e. We'll exponentiate both sides. E to the ln sub e cancels out, so we have 5 over x equals e to the third power, I don't know, 20.086. 20.086. Now, you could multiply both sides by x and then divide by 20.086, and that's great. Also, you can think of these things like a proportion, and you can always just exchange the cross products. So you can just switch the places of the x and the 20.086, making it 5 over 20.086 equals x, which is the same thing you would have gotten eventually the other way. I just wanted to show you something. 20.086 equals 0.249. 0.249 equals x. So same properties as the logarithms, except we're just bringing in this e. E to the ln of x to the third equals 8. Well, e to the ln sub e all cancels out, so we just have x cubed equals 8. And then how do you get rid of a cube? You cube root it. And the cube root of 8 is 2. 2 times 2 times 2 gets you that 8. That wasn't even that bad. Now we're going to be graphing them. Here's the general graph for the graph of e. When you're graphing y equals e to the x power, it shows exponential growth, but again, like e, to the first power is this 2.718. So that'll always be at your 1 and that, unless there's a change. You can see the y-intercept is at 1, and then it just cruises up. If it's a negative exponent, it will show exponential decay. So we're going to graph a couple of these and say the domain and range. So we're just putting in our usual numbers. If we put in 0.75, if we put in -2, let's see what we get. And you can just type it most of the time in, depends on your calculator. You can just type it in kind of how it's written. -2 times 0.75, and it comes out to 0.45. 0.45. If I substitute in -1, I'm not going to rewrite it each time. 2 times e to the 0.75 times -1 is -0.75. Comes out to 0.94. If I put in 0, 0.75 times 0 is 0. E to the 0 power is 1. 1 times 2 is 2. If I put in 1, let's see what we get. Okay. Time out.